All right, so today is Monday, February the 1st. We are going to cover basically a quick crash. Let's not call it crash course, but we are going to cover the fundamental concepts in machine learning. So this class is going to be super important. And so it's going to be only in PowerPoint this week, actually. We will not use Python. So this is you can think of it as an opportunity to build up your skills, to just empower your skills in Python, because the homework 2 is going to be published tonight, and it's another EDA. Okay, so for this EDA, you don't have answer keys. So just make sure that you compare it with homework 3. Sorry, you compare it with your homework 2, and then just make an EDA out of it. Okay, and you have until next Monday. All right, so let's open up the slides, and yeah, we'll see how far we can go. The plan, this is completely new. We didn't cover these things last year. So the reason that I'm telling you is that there's a good chance that I'm not able to cover everything. So I have to adjust my speed according to the class, your feedback, right? So the plan is to cover the first 3 or 4 parts and then leave the parts 5 and 6 for next class. But we'll see how far we can go. Make sure you understand every single concept in this set of slides. This is very, very important. If you know me, I'm not a big fan of memorizing things, but when it comes to concepts of machine learning, I really want you to memorize. First understand them and then memorize them. All the things that you see for class today and the next class. Again, I'm not a big fan of memorization, but this is a different story. If you can figure out, because throughout the semester we're going to repeat many of these concepts again and again. You should know what are those concepts, right? So that's not a time that you go back, look at the slides, and then see what's going on. This is different. Usually for homeworks, I say don't memorize anything because you always have computer. But when I'm reviewing the concepts, you have to know what I'm talking about, right? So memorize. Again, first understand for sure, and then memorize these things. Okay, this is us, right? So we are baby learners in the world of machine learning. And then the first thing we should learn is to basically, okay, because I need to annotate on my laptop. So let me see if I detach this, what happens. I hope that it doesn't disconnect. Okay, so far it's working. Okay. So these are the building blocks of the machine learning concept. And it's not only machine learning, it's also deep learning as well. Basically, in these 2 classes, we're going to see how a machine really learns. What do we mean by how machines learn? This is a very subtle topic. Okay, so the plan for today, we're going to cover these fundamental concepts. The first one, we'll be talking about inference versus prediction. So I think you're all familiar with this distinction between the 2. Any idea what is inference, what is prediction? Guys at home, feel free to unmute your microphone and just participate.
Inference has to do with figuring out population parameters and sampling parameters. You take a sample population, try and figure out what's going on in the population. Prediction is about, based upon what we have here, what's something outside of our data set we can predict. Be that a future time or a different, a different set of explanatory variables. What do we predict in there?
Exactly. So inference, we want to say something about the population parameters by looking at, making inference from the sample, right? So and basically you want to see what's the causal relationship and things like that. But predictions, we only care about, okay, at the end of the day, the thing that you're predicting, is it close to reality or not, right? So this is the difference between the 2. When it comes to machine learning versus econometrics, so I want you to look at these 2 curves, well, let's call it diagrams, and tell me which one do you think is heavily machine learning, which one is heavily statistical learning or econometrics? Yep, Ryan.
The prediction, the machine learning, and then the inference is the econometric.
Yeah, the circle on the left, this is what we do in machine learning, right? So this is basically, it's going to be our machine learning world. And the other one is the statistical learning. We said that in machine learning, we care more about predictions compared to inferences, right? And this doesn't mean that we don't like interpretability. At the end of the day, if you can have a model, machine learning model, which is also predictable, this is really good, right? So this part, this part, the inference part, there's a concept in machine learning, it's called explainable machine learning. So there are models that we call them explainable machine learning, which they are in this. So for example, we have simple regression analysis. So linear regression is here. We are gonna see lasso, Liz regression, logistic regression. These are the models that, even though we can categorize them as examples of machine learning models or algorithms, they're also interpretable. So these are interpretable machine learning. But in general, whenever we are going to work with unstructured data, we know that predictions is the thing that only matters, not the inference, right? Okay, so that's the first concept. Then we're going to start the class by, the first part is going to be the model. So what is that thing that we call it model, right? So what is that thing that's going to capture the relationship between variables that you're thinking about, right? So let's say I have a bunch of variables, then I believe that there's a relationship between the two. I have to start writing it down, right? So what is that model that's capturing this relationship? We're gonna, in a model, we're gonna talk about parameters versus hyperparameters, and then what is parametric model versus non-parametric models, right? So these are very important concepts because the models that we cover in the class, not all of them are the same, right? So because some of them are parametric, some of them are non-parametric, some of them don't have hyperparameters, the other ones has. So we have to understand what are these things, right? So there's a good chance that you haven't seen hyperparameter before, or there's a good chance that you don't know what is non-parametric machine learning models. So we're going to talk about these things. Then in the next part, we will discuss evaluation metrics. So for example, at the end of the day, if I have a regression analysis, how can I compare two models, right? In econometrics, we know that we can look at adjusted R-square. But in machine learning, what are other tools? What about classification, right? So we're going to cover these things as well. Then we will be moving on talking about overfitting, and basically overfitting is somehow it comes from the idea of bias-variance tradeoff. And yeah, this is a very, very, very important and subtle thing because people usually get confused. What is this bias-variance tradeoff? I think Grayson asked a very good question. That was a very deep, very, very good observation that says that when the sample size increases, does bias and variance decrease or what happens? The bias and variance that we're talking about in this class is bias variance for repeated sampling. This is a feature for repeated sampling. So the sample size is fixed and we're going to repeat that, not increasing the sample size. So this is a very subtle point. I'm going to talk about it later on. But I want to make sure that everyone understands what was Grayson's questions when we get to this slide, because this is a very good observation. Then we talk about resampling methods. The idea of resampling methods is that sometimes your training data set is not that large. It's not large enough, right? So sometimes, for whatever reason, your training data set, the part of the data that you're trying to teach the machine with that is small. If the training data is small, what can we do about it, right? So we're going to talk about some techniques called resampling techniques, right? Within the resampling techniques, we will be talking about cross-validation, which I've watched the video, and bootstrap, right? So bootstrap, not necessarily this week, but down the road, we're going to see what is bootstrap. Then, I hope that I can cover all these first 4 parts. So parts 5 and 6 is the topic for next class. So whenever we clear the terminology, I will talk about how do machines learn in general. So this is going to be, I'll put together a flowchart diagram, and then we're going to go over it next class. And then lastly, we will be talking about the solvers, the learners, or the optimizers. These are for models that, we will be talking about loss functions, but sometimes there are some models that the loss function is not, you cannot take derivative from the loss function, or the loss function doesn't have a closed form solution. If you don't know the shape of the loss function, or doesn't have a closed, or it's not differentiable, don't worry, we're going to talk about these things. You have to use some solvers. So gradient descent, stochastic gradient descent, this is AdaGrad, or adaptive gradient descent. Oops. And the last one is Adam. We're going to talk about those topics in next class, right? All right. So that's the plan. Let's see how far we can go. start with the model. So this is the functional form that we can assume for our model, right? Let's say we have, whatever your model is, you can summarize it like this. I have a target variable on the left. So y, we call it response, dependent variable, output, or in machine learning language, we call it target, right? Then on the right-hand side, we have a functional form, right? So this f of x, I showed with f of x and theta. Theta is basically the parameters of the model. So in machine learning language, usually we use theta for parameters. In econometrics, we use beta. So that is just a different name. And x are the predictors, independent variables, input features, or in general features. I want you to learn, just try practice these two terms, right? Target, features, and parameters. So parameters really doesn't matter if it is econometrics or machine learning. But in the machine learning world, people use target, features, and parameters. And we can summarize the parameters. Let me see. We can have multiple, well, let me see. We can have multiple explanatory variables. Let's say we have m of them. We have k parameters. And then we can put it in a functional form. And at the end of the day, we need to add a noise. Okay, so is this clear in terms of, okay. So I want you to think about it. Why do I need to have that noise to the end of the model? Any idea? Why do we have to add epsilon there? Yep, David?
There are some variables or factors that we can't account for with data or different variables and parameters.
Yeah, David is saying that because there are some factors that we cannot control for or put in on the right-hand side. So that's correct. That's more of an econometric word answer. But what else? Does everyone understand his point? So he says that maybe there are some other explanatory variables, or here in this language, feature variables on the right-hand side that we're not including in the model. But I want you to think more widely. This is machine learning. You can add anything. You can exploit all the information. So even, let's say you exploit all the available feature space in the model. So why still do I need to have that epsilon? What do you think? That's noise. So what do you think we have? We should have noise. Okay, guys, the reason is that I always think about this statement. All models are wrong. Some works better, right? We never know what's the true relationship between variables. So that noise must be added to the model because sometimes we have missing variables, sometimes, as David said, sometimes basically all models are wrong. So there is no way that you can pin down the exact functional form which tell you the relationship between the feature space. So that's why we need to have that noise there, okay? So it's all about estimating f by, let's put a hat on top of it, call it, this is the estimated version of f, so let's call it f hat, for two purposes. First one, inference, the second one, prediction. So inference, as we talked about earlier in the class, basically if you want to interpret things, we use inference. If you want to make predictions, basically that's a prediction. In either case, you have to estimate this f by f hat. So the goal, so what does that mean, estimate f hat, the functional form? Imagine I say there's a relationship between, I don't know, education age from one hand and wage from the other hand. And at the end of the day, you want to come up with a functional form that can tell you what is the relationship. Well, let's make it in 2-dimension, right? So I have education and wage, right? So this is our simple regression language. And then later on, we're going to build on top of that terminology. We start with regression, and then we see what else we can cover. So if I come up with a f hat of, here we have x. So this is basically an estimation of the true relationship between education and wage. We're estimating that. So we call it f hat, right? So for example, what is f hat here? So what is my x? X is the explanatory variables, right? Basically, we're saying, okay, what is your wage hat? The predictions for wage is going to be a function of education, right? And if I have guessed that function, if I have estimated that function, so for example, we have beta hat 0 plus beta hat 1, education. So at the end of the day, we have something like this. Is this familiar to everyone, what we're doing? So at the end of the day, we want to estimate this line, right? So we call it f hat, right? So in this example, in this simple example, what are the parameters? Yeah, beta 0, beta 1, right? Or so these are the thetas. We call them beta here. What are the hyperparameters? Oh, well, no. Well, that's for the next slide. So we're going to talk about parameters versus hyperparameters, right? So that's the next slide. But so far, just understand that the goal is to estimate this guy, because at the end of the day, that's the one that tells us what's the relationship between variables, right? All right. Now let's talk about hyperparameters. We know what is parameters, what are parameters, basically beta, in a regression analysis betas. Now let's talk about hyperparameters. Model parameters are estimated from data. And if you compare this one with the previous one, what I wrote here is exactly the same. So I want you to think about it. What is hyperparameter? Model parameters are estimated from the data, basically from the training data. We will talk about it. Automatically, and model hyperparameters are set manually or come out of an optimization that we have to do it manually, right? And so if you look at this, I cannot use my cursor. That's a little sad, so I have to use the pen. So if you look at this, let's say, picture, as you can see, the blue ones are, at the end of the day, we will tune our hyperparameters, right? So the model has a parameter and hyperparameter. At the end of the day, we will estimate those parameters by looking at the training set. So we will estimate these parameters by looking at the training set, and we will tune the hyperparameters by some techniques that later on we're going to learn what are they, right? But I want you to think of an example. Does anyone know a model that you can tell me, for example, these are the parameters, these are the hyperparameters? Yeah, there's a good chance that you haven't seen hyperparameter before, I understand, but I just want to see if anyone has heard. Okay, so let me give you an example. Imagine we have, well, I will stick to that simple example of wage versus education because we're all familiar with and we can relate to. So I'm going to say this wage is a function of beta 0 plus beta 1, education plus beta 2, education to the power of 2, plus, let's say, beta, we have k, education to the power of k, plus some noise epsilon. Okay, now you tell me what are parameters in this example. The parameters are easy, right? So what are the parameters? This is a polynomial model, right? So basically, the idea is that I believe the relationship between wage and education is not that simple line. Maybe it's something like this. I'm bending the curve. I'm bending the fitted line by doing something, by making a polynomial model, right? This is a polynomial regression analysis. We're going to see how we do it in Python, but the idea is very simple. Right? So we're adding education square, education to the power of 3, to the power of 4, and etc. to make sure that that fitted line, I can bend that fitted line. I can make it curved. So what are the parameters here? Beta 0, beta 1, up to beta k, right? What is the hyperparameter? What do you think is the hyperparameter here? No, beta is a parameter, right? At the end of the day, we're going to use the train set to estimate those betas. Remember, in econometric analysis, we did it with OLS. In machine learning, there are 2 ways. So we will talk about it. One is OLS, the other one is gradient descent. But what's the difference? Why we have to do it that way? So we will talk about those things next class. But betas are the parameters. So what is hyperparameter in this simple example? Make a guess, yeah.
Would it be the education squared?
Education is your explanatory variable, okay? So education square is going to be another feature. So education one feature, education square another feature. These are very good points. So what is left?
Error.
No, error is error term. That has a name. What is left without a name? Look at this k. So how do I know that if I should do the polynomial model should be degree of 2 or 3 or 4 or 5? So this is a hyperparameter. So I look at that. The hyperparameters are set manually prior to training the model. So before I train the model, I say, okay, let's go ahead and use this model, education to the power of 2, and ignore the rest. Right? Education to the power of 2. So that's k is equal to 2. Then you look at the output, you compare the results, and then you try with k is equal to 3. You try with k is equal to 4. At the end of the day, you compare, you see which one is best. So basically, you're optimizing that hyperparameter as well. Does that make sense? So some models like this polynomial has a hyperparameter here, in this case, the degree of polynomial. Some models like the simple regression, there's no hyperparameter here. Does that make sense? Okay. So we're going to see, for example, in random forest, SVM, all the models that we cover in the class, there are going to be parameters and hyperparameters. So whenever I talk about hyperparameters, remember, hyperparameter is not something that we call the machine learns. The machine learns the parameters. Hyperparameters that are something that we set manually or we optimize them. Okay.
So when you say set manually, are you saying like you're adding beta to education to the third beta?
Exactly. You stop at 2. So you try different models, right? 2, 3, 4. There are some methods. So we will talk about cross-validation and ELMA methods that figure out which one works best in the test set. All right. So that's parameters versus hyperparameters. Guys at home, any questions? Good? Okay. The next concept is parametric versus non-parametric model. Remember, the true relationship between your feature space and the target variable, the f of x, is unknown. We never, as I said, all the models are wrong. Some performs better, right? So that f of x is unknown. The goal is to see which of the machine learning algorithm that we're going to cover is better at approximating that function, right? So far, good? Okay. Now, an algorithm, and we're going to say that algorithm will learn or estimate that f of x from the training data, right? So we are going to say, okay, I have a data set. This part, let's say 70%, 80% of it is reserved for training the model. And then the 10%, 20%, 30% is used for testing the model, right? So what's the difference between parametric versus non-parametric model? That f of x that we're trying to estimate, oops. This f of x. If I assume some functional form for that, this is a parametric model, right? So for example, regression analysis. What is the functional form in regression analysis? We say linear regression analysis, right? Wage is equal to beta 0 plus beta 1 multiply education. Who told you that you have to make this restrict assumption, right? We say, okay, because we need to come up with some theory, come up with some closed form solutions. We make that assumption and we say that the relationship is linear. So that's what we call parametric model, right? So the f of x is assumed. Example, linear regression. GLM is generalized linear regression. We will see them. Logistic regression, simple neural networks. Again, neural nets are for deep learning, but basically whenever there's one hidden layer, there's no hidden, well, the one layer in between, we call it simple neural network, okay? So does everyone understand what is parametric model? So for example, these two things that we saw, these are parametric model because I'm assuming a functional form. Here I'm assuming a polynomial functional form. Here I'm assuming a linear, well, both of them are linear parameters though, but linear relationship in the fit as well, right? So what are the advantages and disadvantages of parametric models? So one of the advantages is that it's simple, right? Because you have you're assuming a functional form and you observe that f of x. This f of x is something observable, right? So and remember guys, you're making an assumption, right? So that's simple. It's going to be faster. When I say it's going to be faster, what do I mean? Because at the end of the day, whatever model you use, you need to predict, you need to estimate the parameters. If I have a functional form like this, or like the other one, in regression analysis, for example, I can use OLS, and OLS, the answers for beta hat 0, beta hat 1, beta hat 2 has a closed form solution. I don't need to just look around and start from a random number. I can solve for the solution, right? So that's because the f of x is known. So that's part of the parametric model, right? And so it's faster, it's simpler, and it requires less data because when there's a closed form solution to your to the parameters that you're estimating, You may need less data, right? Remember, in econometrics, if I have a data set of size 20, I can still calculate beta hat 0, beta hat 1, and etc. Right? Okay, so those are the advantages. What are the disadvantages? It limits the complexity of the model, right? Because if I'm assuming the linear relationship, I cannot go beyond that, right? So it will do something that your model is not flexible enough. And we'll talk about flexibility later on. So for example, if you want to have not only linear relationship, but nonlinear relationship, but interactions, but hierarchical, right? So these are all the things that simple linear model does not cover. So your model is not complex enough. You with me? You good? Okay. Then what is the non-parametric model? So in non-parametric model, f of x, this is subtle. This is really subtle. I want you to pay good attention. F of x is not assumed. We do not make any functional form restrictions on f of x. And again, this is something that usually students have a hard time understanding it, because you have to say, okay, what is f? So how the model, if this f is not restricted, how the computer is able to solve for that? Well, the idea is that this f of x can be free to be any functional form, right? So it can learn. Basically, let me give you an example. I'm going to give you 10 inputs, 10 outputs, right? So maybe the inputs are give you 2 columns of data, and the output I'll also give it to you. So for example, I say, let's say these are the columns for the inputs. 1, 1, the output is 2. 3, 5, the output is 8. 4, 9, the output is 13. So you realize that what I'm doing behind the scenes, so I'm adding them together, right? So sometimes I put a restriction. I say that, okay, go ahead and only think of linear relationship between these 2 columns that you're passing, right? Sometimes I say, do whatever you do. Just figure out what is the pattern. Learn the pattern, and then you're not restricted to use linear model. You following? That was a very simple example, but we're going to see the models that we cover in the class, like KNN, K nearest neighbors, CART, classification and regression trees, random forest, SVM, deep layers with deep neural networks like ANN. These are the non-parametric algorithm. So what is the advantage? Flexibility. So they're going to be a lot more flexible, right? Because we're not imposing any restrictions. Performance. So this one usually, it's not always. Usually they perform better than the parametric ones because they're more flexible. But it comes with a cost. If you make your model too flexible, they're going to overfit the data. Okay? And we will talk about those in the next slide. What is the disadvantage? It's going to be slower. It requires more data, and it may overfit, right? Why is it slower? Because this is really important, guys. This f of x, we're not imposing any restriction. We cannot come up with a closed form solution for the parameters at the end of the day. So this means that we have to work with some optimizers. So let's say, make a guess, calculate everything, calculate the error, and then if the error is large, go back, make another guess, go back, make another guess. So this is the concept of gradient descent, for example, right? So for that reason, it's going to take a lot of time. And imagine your data set has millions of records. So a parametric model with a closed form solution is going to be a lot faster than a non-parametric model. Is this part clear? Because this is important. I want you to, so this is the part that I want you to memorize. So what are the examples of non-parametric in machine learning? KNN. Because next class, we're going to start with regression and polynomial, so you know that it's parametric. So whenever I want to calculate the betas, I can do either gradient descent or use OLS, our old friend OLS, right? But when it comes to non-parametric model, KNN, CART, random forest, SVM, we cannot, it's going to be slow and lots of other things. But I just want you to remember which one is parametric, which one is non-parametric. All right. Okay, so let's move on to the second part, evaluation metrics. So this is, I only have one slide for that because for every model that we do, we are going to have our own evaluation metrics. But I wanted you to watch the confusion matrix because usually students haven't seen the classification evaluation matrix that so the concepts of false positive, false negative, true positive, true negative. But in general, for supervised learning, we can have evaluation metrics. For unsupervised, we cannot evaluate. Does that make sense? So why we cannot use evaluation metrics for unsupervised? What do you think? We don't have labels, right? With unsupervised learning models, we have no idea what we're doing at the end of the day. We cannot, we have no idea. We cannot be sure if it is a good thing or bad thing, right? So that's why evaluation metrics are used only for supervised learning models. And of course, the reinforcement learning as well, because it's labeled, but that's a separate story. So in general, we want to compare how close are the predictions, the y hat at the end of the day, right? That comes out of that f hat, which is estimated. How close are they to the actual numbers in the test set? This is really important because at the end of the day, in the machine learning world, I don't care if the model is fitting the training data set or not, because it will. I can use a lot of information in the training data set, and I can make the model very flexible to the point that there is no part unexplained anymore, right? So for that reason, we don't care about the evaluation metrics in the train set. We only care how our model is performing in the test set, how the model is performing on something that the model hasn't seen before. Because the model has learned the pattern from the training set. So it's not good if I test it on that set, right? Because it's going to be biased. So we are going to see how does the model perform in the test set. So this is really important concept, train set versus test set. Is everybody following? Okay. So then it depends if you're doing regression analysis or classification in general. So regression, when your target variable is continuous, we do regression. When the target variable is discrete or dummy or binary, depending on how many classes we have, it's going to be classification, right? So we talked about these concepts before. But here's a laundry list of the evaluation metrics that we can use. But usually, when it comes to regression analysis, we look at MSE, mean squared error. When it comes to classification, we look at the misclassification rate or accuracy, but that depends. We will talk about so later on. So we already know what is confusion matrix, right? There are true. We had something like this: predictions, positive, negative, actuals, positive, negative. Then we have true positive, true negative, then false positive, false negative. So if you again, don't worry about. I hope that you watched the video, but this is something that we're going to cover in very detail later on, because out of this simple confusion matrix, we are going to figure out what is accuracy, what is precision, what is recall, what is F-score. So these are all the things that we're going to cover in classification. But I just wanted you to have some idea what is confusion matrix and what do we mean by that. Okay. Then we will look at ROC, AUC, and then these are for random forest that we are going to talk about later on. So here, when it comes to regression, this is the best one. We can use absolute error as well, but this one to mean squared error and residual, not residual, root mean squared, the square root of that. So these are the ones that we will look at in the regression analysis. So these are basically the metrics. Okay, is it clear what we're doing? So at the end of the day, we have a training set. The model has been trained by using the information from train set. The parameters has been estimated. And then you're going to test that model in the using the test set. How do we say that if a model is doing a good job or bad job? Looking at the numbers here. Okay. If it is, for example, if it is classification, if accuracy is high, it's a good model. If accuracy is low, it's a bad model. If MSE is low, it's a good model because it means squared error if the errors are small. If MSE is high, it's a bad model. Okay. So that was the second part. Now let's talk about bias-variance trade-off. Okay, so here, this is a very small version of the table that we saw in class 1. And I encourage you to memorize that one. And I re-emphasize it that, again, understand and memorize these things, because it's important that you know what's the difference between econometrics, statistical learning, and machine learning. Okay, so let's talk about some advantages of machine learning over statistical learning, and then this discussion should lead to the concept of overfitting. So the advantages of machine learning is what? It has the ability to uncover complex interactions, right? Because again, think of that word that you're not imposing any functional form. You're not saying that the f of x should be linear. It can be anything. So it's going to be more flexible. Because it's more flexible, it can find the patterns better in the data compared to statistical learning, right? Then another advantage is that it processes massive amounts of data quickly. Again, we're going to talk about the optimizers later on. Capture nonlinear relationship, no surprise, and predict the structural changes between features and the target. And basically, it says that if there's a structural change, let's say before 2010, if you look at the financial data, before 2009 and after 2009, maybe there's a structural shift in the interest rate, right? After the QE, the interest rate dropped. So maybe the monetary policy was not as effective as before. So this is structural changes is going to be captured by machine learning, right? Again, econometrics can also capture those things, but machine learning is going to do a better job. What are the disadvantages? So it can produce overly complex model, right? Because before you know it, you're making your model super complex because you get excited. The model is doing a perfect job in the train set. You get excited, you make it more flexible because it's doing a better job. But remember, if a model is doing a good job in the train set, this does not mean that it's going to necessarily a good job in the test set as well. Back to your question, Abraham, we're going to look at some charts, and I'll show it to you. What do we mean by that? If I make the model super complex, super customized, maybe the model is going to work only for that train set. If I pass a new train set, the model is not going to do a good job. Does that make sense? And let alone for the test set. So for the test set that the model has not seen, it's going to do a poor job. Machine learning is difficult to interpret. So again, that depends on what model are we using. So if someone tells you that machine learning is not interpretable, after taking this course, you have to take a pause and say, what machine learning algorithm are you talking about? Are you talking about regression, linear regression? That's perfectly interpretable. Are you talking about decision trees? That's perfectly interpretable. Are you talking about random forest? Yes, I give it to you. It's not interpretable, right? So you have to be clear. What model are you talking about? Because we have an interpretable machine learning, the first slide that we talked about as well. And sensitive to noise. This again, sometimes at the end of the day, you're making the model so complex and flexible that it's not learning anything. It's basically memorizing. It's capturing the noise. Okay? So your model should not memorize the data. You should not memorize the train set, because if it does, it's not going to do a good job in the test set. Right? So that's what we mean by sensitive to noise. And finally, it can overfit, because if I make that model super flexible, it's going to do a perfect job in the train set. We call that concept overfit. And that comes from, again, the continuation to that concept is a bias-variance trade-off. Okay, so let's see where does this overfit come from. So overfitting happens when the fitted algorithm does not generalize well to new data. This is understandable, right? So imagine you have a model. If you cannot generalize that model when you use a new data set, basically your model is doing a poor job in the test set. Again, in the train set, it's doing a perfect job, but in the test set, it's not doing a good job. So let me give you some examples. I want you to look at these three graphs. The data is fixed, right? So the bluish, what is it? Green, bluish, let's call it green. The green dots are the data. And it's the same in these three different charts, right? But look at the first one. This is a linear regression, right? So the first one, we have an upward sloping line. So this is a very simple, super simple model, right? And then we say, okay, we're going to talk about the bias and variance of this model later on. But I just want you to pay attention to the concept, what we're doing. As I go to the right, am I making the model more flexible or less flexible? You're making the model more flexible, right? So it seems that, and guys, remember, this is train set. This is train set. In the train set, it seems that model number 2 is doing a better job than model number 1. Does everyone see that? Because it's capturing the relationship better. Can we do even better? If I make the model more flexible, does everyone agree that model 3 is a lot better than model 2? Because again, guys, this is a train set. In the train set, model 3 is capturing everything, literally everything. So if I look at the R square, it's going to be what? 1, right? 100%. So, but do you think that this is a good model? So why do you think that it's not a good model? Yeah.
Well, if you use any other data, it's not going to match.
Perfect. Perfect. So I want you, so Grayson, this is back to your point. I want you to realize whenever we talk about bias variance trade-off, We're talking, these are the properties of repeated sampling. The sample size is fixed. Can you see that? The number of green dots are fixed. So when I talk about the model variance, model bias, I'm talking about the repeated sampling, right? So imagine these are, let's say these are 20, I didn't count them, right? So let's say there are 20 green dots. The idea is that if I use another sample now, it's not going to be that exact 20 dots, right? So then this model for sure is going to do a bad job because maybe these are the new 20 dots. Are you following? It's going to do a poor job. However, this model, it seems that it has a balanced combination of flexibility and working better using another data set, right? So this is an example for regression. Here's an example for classification. Are you guys familiar with this graph, with this chart? The classification versus regression. So actually, let me, because when we do this visualization in Python, usually students think that on the y-axis we have y. No, in regression analysis, yes, this is my y, this is my x. In classification analysis, we're talking about two different features. So this is my x1, one feature, this is my x2, feature number 2. Where is y? Y is the shape. Is the shape of those. So so y can, look at that, y in this example can be either circle or cross. Does that make sense? So it's as if you're looking at the 3 dimension. Does that make sense? So just pay attention. Whenever we talk about things like this, x1, x2 are 2 features, but when we do regression in 2 dimensions, it's x is x, y is the target. So that's a big difference. So again, we have classification. Imagine, I don't know, imagine this is my class. Historically, the train set of my class is the last year machine learning students, right? That's the train set. And at the end of the day, I predicted that if they pass not pass, of course everyone passed, if they get an A or not got an A, right? So if the previous student got A, I showed them with circle. If they got not A, anything else, I showed with cross. Is everybody with me on that example? Okay. And this is a train set. So it means that these are the students from last year. At the end of the day, I want to make predictions for you guys, the current students. Let's say X1 or X2. X1 is the study hours. X2 is, average homework score. Okay. So what does it mean? If study hours is high, homework score is high, most probably you get an A. If both of them are low, most probably you get a not A. Right? Does that make sense? All right. Now let's look at these 3 models. And by the way, guys, we call this line classifier, right? So that classifier can be logistic regression. We will talk about these things, right? Logistic regression, SVM or SVC, KNN. We're going to talk about all these classifiers later on. But at the end of the day, you can visualize it like this, right? So here, my classifier is perfectly linear. And at the end of the day, I say if it is to the right-hand side, let's call it circle. If it is to the left-hand side, let's call it cross. This is a very simple linear classifier, right? Then let's make the model more complex. If I make it more complex, it says that, you know what? Your classifier should not be linear. The classifier fit was nonlinear. Do you agree that it's doing a better job? If you count the misclassifications, maybe it's doing a better job. Does everyone see that? Let's make it even better. Look at that. What's the accuracy of the model on the right? 100%. Because in the train set, it's doing a perfect job. But do you see how flexible that classifier is? So again, the same story. Which one is better? Most probably model number 2 is going to be better. Why? Because it's incorporating 2 effects. The one is that if I do repeated sampling, does it do a good job? So that we are going to give it a name, we call it variance. Or on average, if I'm hitting at the target or not, so we call it bias, right? So let's summarize these things and put it here. Well, so that's the next slide. This is basically the concepts of overfitting. So the model fit the training data too well while not predicts. So this is the definition of overfitting, right? While not predicts well in the new data, right? So basically this model and this model. So this is a regression. This is classifier. Both of them are overfitting, right? No surprise. Now, how else can we say that? So the model fits the noise that epsilon in the training data, right? So find a pattern that does not exist. So maybe the true pattern was not. Do you agree that this is noise? The true pattern in the data may be something like this. This is more like, well, I have to bend it. To me, this more likes a true pattern. The rest is noise, right? So overfitting means that you're fitting the noise, not data. Okay. Then another way of saying overfitting is that the algorithm has simply memorized the data rather than learning from it. So when I say the algorithm is learning from the data, what does it mean? It means that by looking at this model, let's say regression model, when I say the algorithm learns, what does it mean? It means that what is beta had 0, beta had 1, beta had 2. Does everyone see that? Because it's a polynomial maybe with a degree of 2. And what is the sign of beta had 2? Positive, negative? What do you think? Is it convex, concave? I'm just checking out your background in mathematics. This is concave, right? So if it is concave, what is the sign of beta hat 2? What is the sign of the coefficient of x squared? It's negative, right? Okay. So what I'm saying is that maybe y is equal to 1 plus x plus. So here it should be negative minus 2x2. Something like that. Okay. All right. Okay, and then finally, the model is too complex. So these are all different ways of saying that the model is overfitting. Okay.
Just to go back to what you said about it doesn't learn, it memorizes. So you're saying that in the example you used, you can identify the parameters?
It can, yeah. Well, yeah, it's a good point, Abraham. Even though, so he's saying that, what does it mean? Does it mean that it cannot find a parameter? It can. It can pin that. Maybe this is a polynomial of degree 15. I don't know. With beta 1 through beta 16, does that make sense? Yeah. But it can find them. Okay. But we know that it's useless, right? Because if I do another sampling, it's going to do a bad job. So the concept of bias versus variance is a concept which applies to repeated sampling. So I keep saying that because when you look at the learning curve, you think that we're going to talk about learning curve later on, but as a sample size in the train set increase. So this is Grayson's question actually. He asked well, let me actually cover these two slides and I'll come back to that question because that's a very deep question. All right, now let's talk about MSE decomposition. So MSE, again, we have different metrics. One of them is MSE, mean squared error, and that's a metric for regression analysis, right? You can simply replace this MSE with any kind of loss function. So for example, if it is random forest, we're going to do cross entropy or Gini. These are different loss functions that we're going to use. But here, let's keep it simple. Let's keep it to something that we are all familiar with. We know from our regression analysis, we know what is residual sum of square, what is mean squared error, and things like that, right? So, and let's go over the concepts of bias-variance trade-off. This is one of the core concepts in supervised learning, right? Assume that the data is generated by a simple model. And of course, I have to add this noise too. This is the model. And what does this mean? What is the distribution of noise? Then the expected value is 0 and variance is sigma. And we have only 2. So this is going to be normal, right? The noise is normal. So when the distribution of your random variable is pinned down by 2 numbers, average and variance, so that's going to be normal distribution, right? So basically it says that your errors are normally distributed. This is an assumption, okay? Then the estimated model is f hat. Remember, this estimated model is the one that the machine learned from looking at finding a pattern in the train set, okay? So this part, I don't want you to necessarily follow the mathematics, but at the end of the day, we're going to say that mean squared error. So what is error? Error is y minus y hat. Do you guys remember? This is the error, right? So what is the difference between actual versus predicted? Mean squared error. Square it, take the average. So this is mean squared error. Or I can say expected value of these epsilon squares. So does it make sense? And of course we have to predict it. So this is our mean squared error. Are we good so far? Definition of mean squared error. The idea is that I can open up the definition y minus y hat. So y hat, I can replace y hat with f hat, right? This is my y hat. This is my y hat. And then I can replace y with f of x plus delta because it comes from here. plus epsilon, sorry. Then I can play around with the equations. At the end of the day, I can, again, if you're curious what is it, how the proof works, just Google it. MSE decomposition, you can find the proof. But here, at the end of the day, we can decompose it into 3 parts. The first part, variance of the model. The second part, bias, we call it model bias. Mathematically, it's bias to the power of 2, but let's call it model bias. And then the last part is this. This is the irreducible error part. And this means that you cannot do anything to the model that take this error away, because that comes from missing values and things like that. That's why we call it irreducible part. Okay, so keep it simple. Again, I just want you to realize that we can decompose MSE like this, and so maybe next slide is going to be more helpful. And as I said, this MSE can be replaced by any loss function, right? So not necessarily for regression. We can revisit these concepts when I get to classification models. But the idea is that the error, think of it like this. Some function of the error on the left-hand side can be decomposed into 3 parts: model variance, model bias, irreducible error. The model variance is the variance if you had estimated the model with a different training set. So this is something that you all figured it out, right? When I asked that question, so what if you use another sample? So the model variance, again, this is the variance if you had estimated another training set, right? If I do another training set, I get another. So going back to that plot that we had overfitting, we said if I use another training set, it's going to be different, right? The model is not going to do a good job. So that's the model variance. The model bias is the error due to using an approximation of the model, right? Guys, remember, at the end of the day, we don't know what is that f of x. If the model is too simple, then the bias of the model is going to be high. Because what is biased by definition? On average, are we hitting at the target or not, right? On average, am I getting close to that unobservable f of x or not? So that's the definition of bias, right? So if the model is too simple, we know that even in the trained set, we're not going to do a good job. The third one is the irreducible part. So this is due to missing variables and it cannot be fixed by modeling. Okay, so what's the goal? The goal is to, whenever at the end of the day, when you want to compare models, you have to look at the test set and see how the model is doing. And in the train set, the goal is, that test set, the goal is to come up with a combination of model bias and model variance, which is the smallest. So basically, the model which has the smallest MSE in the test set is going to be the best model. Does that make sense? If it is classification, the model with the smallest, let's say, cross entropy, the model with the smallest gene. These are different things that we use for classification. So this is known as bias-variance trade-off, because reducing one will lead to increasing the other one. This is really important, guys. Grayson, did that answer your question?
Yeah.
Okay. So Grayson's question was that, actually, I did, maybe students don't know. So he said, okay, if the sample size in the training set, pay very good attention, guys. If a sample size in training set increase, does the bias and variance increase or decrease? So what do you think? From your econometric course. Both of them or one of them or how? Variance will decrease. What about the bias? The trade-off? So that's what I was saying. This bias-variance trade-off is a property of repeated sampling. The answer is no, both of them. If you're increasing the sample size, both the variance and bias is going to decrease. Because remember, guys, that was my quote last year. Give me large enough data, I can prove anything. If you increase the sample size, I can hit right at the target. And what does it mean? If you look at the variance of beta hat j from econometrics, it's going to decrease if I'm using more data. Well, what about the bias? Of course, the model is going to be more accurate. I'm predicting the chances that I'm hitting right at the target is going to be higher. So the bias-variance trade-off, the trade-off only applies to repeated sampling, not increasing the sample size. Increasing sample size is the concept of consistency that we covered in the regression analysis. Yes, I can say something about the consistency if estimator is going to converge to the population parameter and etc. But this is machine learning work, guys. Repeated sampling, this is how we define the bias and variance. Repeated sampling, not increasing the sample size. This is a very, very good question and very good observation. All right. So choosing the flexibility of f hat of x will amount to a bias variance trade-off, right? So I think you can easily understand this slide now. From left to right, I'm making the model more complex, more flexible. If I make the model more flexible, what will happen to bias? What do you think? If I go from left to right. Does everyone see that this model has very high bias? Because on average, I'm not capturing the pattern, right? I'm not hitting at the target on average. So the bias is high. What about the, well, let's talk about the bias first. Then maybe this is low bias, and this is, what about this one? This has the smallest, well, again, it's capturing, but it's some kind of overfitting, right? It's overfitting to the data. So as we go from left to right, does everyone see that the bias decrease? Right? As I make the model more complex, more flexible, the bias is going to decrease. Now, what about the variance? So, guys, think of the word of repeated sampling. So if the model is this line, if I use another set of data, let me use these dots. Yes, the line is going to tilt a little bit, but not that much, right? Does everyone see that? So the variance of from the left, the variance is very, very small. When I make the model more complex and more flexible, what will happen to variance? The variance is going to be a lot higher, because if I do another sampling, let's say these are other sampling. What is the new model? If I want to do it the same way, this is the new model. So what's the difference between the first one and the second one? A lot. So the variance of the f hat of x is going to be a lot, right? So I hope that you understand. When you go from left to right, the bias decrease. So this is what we are showing. When we go from left to right, the variance increase. This is what we show here. What's the optimal point? Somewhere in between. Okay. So this is what we call. This is a model with optimal amounts of bias and variance. And I can, again, we're gonna plot all these things in Python. And you'll see that we're gonna plot actually the total test error and see how it compares, what is the optimal level of, for example, different hyperparameters in the model, and etc. What I want you to really pay attention is this one. This is test error. If I want to plot, actually, here's a question for you. If I want to plot the train error, how does it look? So I'll give you options. Option number 1, option number 2, option number 3. If I want to plot the train set errors, when I make the model more flexible and more complex, what will happen to train set errors? It will decrease. Eventually, what is the train set error? Look at this one. What is the error here? 0. Right? So this means that if I want to plot the train set error versus flexibility, it converges to 0. So that means that it's not a good idea to look at the train set error. So this is wrong. You want to look at the test set error. Because at some point, you see the test set error is going to increase here because it's super flexible for the train set, not the test set. Okay, these are important concepts, guys. So if you have any questions, just let me know. Okay. And I think the most important takeaway was that the bias variance is a concept for repeated sampling. All right. Again, here's another representation of the bias variance trade-off. This is a bullseye kind of curve. And if you see something like this on the internet, don't be surprised that people show bias variance trade-off like this. So on the top left, we have low variance, low bias, right? So go back to your econometric course. What is bias? Hitting at the target. On average, we're hitting at the bullseye here. And the variance is also small, right? So this is ideal. This is ideal. We can never get to this point. And then let's look at the worst case. Worst case is that bias is high on average. If I take the average of all these dots, where's the average? So on average, we're off. Do you agree that maybe here's the average? So on average, we're off. So bias is high. Look at the variance. The dots are spread out. This is the worst case of the both words, right? So and then we can have low bias. On average, guys, if I take the average of these black dots, on average, it's hitting at the target, but the variance is large, right? Or here, my average is completely off, but the variance is small. Okay? So there's a trade-off between, so that's why what we call the trade-off between bias variance. But what is the optimal? So somewhere in between is the optimal. All right, we good? Okay, let's move on. Let's go to the resampling part. And I really doubt that I can finish it, but let's see how far we can go. Okay, so you already know what is train set, what is test set, but let's see what is validation set. What do we need that? So we didn't talk about validation set at all yet. So typically we can divide the data in the machine learning world, we can divide it into 3 non-overlapping sets, right? Of course, it should be non-overlapping because if there's the term for that is leakage. When there's leakage between data sets, then the model is going to cheat when it's going to report the numbers in the test set, right? If there's a leakage between test set and train set, so it's cheating. So that's why it should have non-overlapping samples. So what is train set? The train set is used to train the model, not surprisingly. So for example, this universe has 1, 2, 3, 4, 5. Let's say it has 100 observations. So we have 20, 20, 20, 20, and 20, right? So the train set, the first 60, is used for training the model. So the machine is going to take this data and learn the pattern. What does learn the pattern mean? Estimate that f hat of x, right? Learn the pattern from the data by looking at the train set. Are we good so far? Okay. The validation set, we use validation set for validating the model and tuning the model. So basically, we are going to tune the hyperparameters of the model here by using a validation set, right? So for example, if I want to see what should be the right polynomial degree, so I tune the hyperparameter, I call it tune hyperparameter, by using this 20 observation. Because so there are 2 things happening here. I don't want to cheat. I don't want to use I don't want to tune the hyperparameters by looking at the train set. Because in the train set, the model is going to learn the parameters. What are the betas? Then I know what are the betas. Then I'm going to see, okay, what is the best number of polynomial degree? I'm going to use a validation set, right? So this is why we use the validation set. And finally, what is a test set? We also call it holdout set. Use it for testing the model. Definitely, we want to test the model on something that it hasn't seen before. Think of it this way, if I want to make a prediction of you getting an A or not, you're my test set. Your model has never seen you guys because the model was trained on last year's students. Okay. So this is really good ideal. Yeah, in the ideal world, if I have millions of records of observation, if I have millions of records of training set, I can say, okay, let's take 20% of it as a validation set, right? And then this is the best way. This is ideal that I can tune the hyperparameters using a validation set, find the parameters using a train set, and then test the model in the test set. But the problem is here. A large data set is needed for this approach. So we call it a validation set approach. If you read the ISLR textbook. But what if you don't have it? What if you only have 100 observations? Look at my example. I only have 20 students last year. This is my only observation. So if I want to say that, okay, take, I don't know, out of that 20, 14 of them as a train set, 5 of them as a validation set, and maybe 3 of them as a test set, the model is not going to learn anything, right? So for that reason, when the train set is small, we have to resample from train set. So this is the idea of resampling. And it's very powerful. The resampling idea is one of the most genius things, I think, breakthroughs of the statisticians. And I always get excited when it gets to this part. So even it's my econometric class when we do bootstrap, or in this class when we do cross-validation, because this is genius. I want you to realize what's going on, why I keep saying that this is genius. Ex post that how these methods work. So what is the motivation? My trained data set is small, and I want to leverage that small data set. I want to use that small data set, trained data set, but I use it multiple times. The same small trained data set. So this is synthetically, I am making my data set larger, synthetically. Is it going to be perfect? No. But is it going to work? Absolutely. It's again, the idea of bootstrap is a miracle, in my opinion, is one of the miracles in statistics. And cross-validation, of course, is a genius way. Okay, so yeah, I have 5 more minutes, so let's continue because.
One question on that.
Yep.
Is it like an appropriate ratio for training set to data test data set, or it really doesn't matter?
Usually in application, we do 70 to 80% for train set and 20 to 30% for test set. There's no validation set. So we're going to talk about it.
Right.
So far, we know why these three different sets may not work, because maybe the train set is small, right? Let's see what are the consequences of that small train set, and then what's the solution. So the solution is cross-validation, but let's go through the bullet points. So sometimes we cannot afford to split the data in three sections because the algorithm may not learn anything from small train set. Remember, the algorithm is going to learn from train set. If the train set is small, it's not going to learn anything. Then if the validation set is small, so a small validation set is also problematic. Why? Because we cannot tune the hyperparameters properly. Does that make sense? So what's the solution? The solution is combine the two. So train set, validation set, combine the two, and then just call it train set. And then the whole out sample is going to be remained as a test set, right? Now I can hope that my last year students, maybe 20 observation, maybe the model can learn something from that 20 observation. Maybe 10 was a small, 15 was a small, maybe 20 is better. Okay, these are very simplistic examples, but you get the point. For example, when it comes to deep learning, we're not talking about 10, 15, 20, right? We're talking about 10 million versus 11 million versus 15 million. So the more data we have, the better. Okay, now let's see. Again, the goal is to obtain additional information about the fitted model. For example, the estimate of the test prediction. Guys, remember, at the end of the day, I want to come up with some estimates for some metrics. For example, what's the error rate in the test set? You're not interested in the evaluation metrics in the train set. We're done with that. So I want you to be very careful about this concept. I want to estimate what is my test set error. So sometimes you're going to say that if your test set error is, so this is a very subtle point. I'm going to stop here. If my test set error is also labeled, then I can exactly observe the test set error. But if the test set error is not labeled, like this class, I don't know what's your score. Right now, I don't know what's your score. So the test set is not labeled. So I cannot calculate the accuracy for this class. So what can I do? I should approximate this number by looking at the train set. Are you following? So this is really, really important. So in machine learning, if your test set is also labeled, that's fine. You can observe that test set error. But in real world, like this example, I want to predict if you get an A or not. Where are my labels in the test set? No, I don't know. But do I have labels in the train set? Yes. I know the previous students got A or not A. Is this clear? Okay. So let's stop here. So this is the idea of cross-validation. We're going to talk about the steps of cross-validation next class. And let me see. And basically, we talk about time series cross-validation, basically done. So we can answer the question of the day, actually. So from the concepts that we talked so far, what is the best? What does this picture represent? This is overfitting, right? It is. So Abraham, to your point, it's working perfectly in train set. But if I sleep differently, it's not going to work. Repeated sampling. Okay. If he himself or she, I don't know, the day after tomorrow sleeps the other way, it doesn't work. Okay. Repeated sampling. The sample size is the same, but we are doing it. Think of it as a repeated sampling. All right. So I think we're good in terms of time. I should be able to finish next slides. On the next class. And guys from home, do you have any questions? And again, please watch this video multiple times and go over the slides multiple times. And after understanding it, memorize it. Because when I get to different models, it should be on top of your memory that what are we talking about? So what are the parameters? Is it parametric? Is it non-parametric? And when it comes to gradient descent, the argument is going to be a little more challenging. So for example, we can solve the parameters beta hat 0, beta hat 1 in regression analysis using 2 methods, OLS or gradient descent. We should get the same answers. And that's where you see the beauty of computer science, how without knowing OLS, I can find the beta head 0, beta head 1 using some computer algorithm. That's the key takeaway for next class. All right. So I hope you enjoyed it. So I will see you next time. So let me pause the recording.